wind up a bit on the top-down search. It's really important, although I think we've got it done pretty well. What I'm going to do is just review it. So let me write the rules again. So you have, actually what I'm going to do it with is stickers rather than paint. I think that works a bit better because we're taking things off and putting them on. This is stickers. So the first thing you do is put a green sticker and the token. And that's how you initialize it. So that's all. There's just one green sticker or green paint, same thing, and a token on the start state, and then you go. So next. So if at any time you find the token is on the start state, actually it'll be back, because most likely they've moved off and come back. If you find the token is on the start state and there's a red sticker on the start state, you halt and announce failure. The next rule is if on a green stickered one state, and you halt with win. Okay. If the token is on a green, I'll just say green state, and there is an unstickered path to an unstickered state, what you do is you take it, I shouldn't say a path, I should say an arc, an edge, arc. So if token is on the green state and there is an unstickered arc to an unstickered state, take it, the arc, and sticker both green. So if token is on a green state and no such arc, re-sticker token state red, token state red, non-start red state. Move back on the green arc and re-sticker it red. And that's it. Now this is a pretty high level abstract. This isn't even pseudocode because we're talking about arcs and stickers and moving. I'm sure that you could all turn it into at least pseudocode and then real pseudocode and real code if you knew how the thing was being represented. But this is a pretty high level of abstraction. That gets a lot of the details out of the way. Now, the claim is, let's say if the puzzle is not solvable, it will halt and fail. And if the puzzle is solvable, it will halt and win with the solution green stickered. So you'll have this situation here. You started here, the token ends up here in a one state. And what will happen is that there will be a path, it might not be very long, there will be a path from the start state to the one state that the token is on, and the nodes and arcs of it will be stickered green. And furthermore, nothing else will be green stickered. That's quite a nice picture. So you just completely read the solution on it. So these are more claims, and the idea is I'm going to write down some claims that individually you're persuaded of because you can see how they're going to be preserved, and together they'll prove this correctness. So this is a as I say, non-trivial because we're talking about, see, solvability. You have a quantifier, it's solvable if there exists a path. You're quantifying over all possible paths, which, as you found out when you're probably doing the exercise, there's an awful lot of paths, even a small graph. So that's quite a powerful quantifier there. And yet nowhere, see, nowhere in here do we have lists of paths. We're not generating a big collection of paths and looking at the paths one by one. We're just dealing with nodes and arcs. And yet somehow we've managed to effectively examine all paths. So that's what's interesting about this. So the first one is that if a node is green, it is on a green path from the root. Now, does that look plausible? So if any node, not necessarily the one the token on, if any node is green, then there's a path from the root, a green path from the root, where all the edges and nodes on the path are sticker green that leads to there. all you have to do is look at under what circumstance does a node get a green sticker. Well, this is the only place a node gets a green sticker, and sure enough, the only way that happens is the token's on a node with a green sticker, and here's an unstickered node and an unstickered path, and we move the token here and sticker them both green. This one has just received its green sticker, so sure enough, it's also on a green path there. That's the only time. Node state, node equals state there at the same time. Exactly the same thing. Sometimes I use one, sometimes the other. The same is true of the text. If the token is on a green, I'll call it state. Well, now we know there's a green path to where the token is, and in state, then the path to this state is all that's stickered green. Now this one states the purpose of the red stickers. It says you're wasting your time. This is not true. Here's what could happen. You start here, turn it green, and then you follow here, and turn that green, and then you follow here, turn it green, and then follow here, turn that green, and then you choose, here are the possibilities, and let's say you've already, these are reds, you've already investigated them. So what happened is you look down here, no joy there, look down here, no luck there. The only other possibility is to jump here, but that intersects the path at an earlier stage. Now, remember, we don't want to waste our time. There's no point, this is already under investigation, so there's no point putting it under investigation again. So the corrected form, the naive one, isn't true. So the corrected form is there's no loop-free path from the start state to a one state. In other words, there's no loop-free solution that passes through a red state once it becomes red. There can be solutions, but they're not going to be loop-free. And you're not really interested in solutions with loops in them. So red states can be part of the solution, but a redundant parts are an appendix of the solution.